Okay, right. Hello and welcome to this month's edition of Tech Talk, where Alex Koizikoff and I are pleased to welcome our guest this month, Simon Nicholson. Now, Simon is the COO of Metascube Limited, who were established in 2016, and they've seen some great success since that time. Now, Simon himself wears many different hats and has qualifications, knowledge, and in-depth experience across the range of business leadership, business development, relationships building, sales, product, and project management, to name but a very few of the many skills he has in his arsenal. Metascube have collectively over 50 years' experience working for a wide range of companies from startups to SMEs to multinational businesses across a wide range of market sectors, both in the UK and internationally. I'll hand over now briefly to Alex to introduce himself for those who haven't seen this podcast before. Then Alex will hand back to me to do likewise, and then I'll open the floor to Simon for a proper introduction to who he is and what he's up to. Over to you, Alex.
Yeah, thanks, John, and thanks for the time today, Simon. Very nice to meet you. I'm Alex, co-founder and CEO of Natreon. We're a battery technology company based in the US. I've been around for about 5 years, and we specialize in solid-state battery technologies, enabling higher safety and performance, especially for electric vehicles and other applications. We're kind of in a growth stage, rapidly scaling production, and hoping to get to the market in a meaningful way with some of our automaker partners in the next few years. So it's a little bit about us.
Thanks very much for that, Alex. Again, I'm John Tuck. I'm a holistic energy scientist representing Silent Koala. I've got over 20 years of experience in the energy generation and storage industry, having started in fuel cells back in the early 2000s and progressed through supercapacitors and then into energy storage devices and batteries in general. I work predominantly in intellectual property for a battery manufacturing company in the UK, and I'm a consultant and advisor to startup technology companies. Now, I've known Simon for many years now, and amongst many other things, he's one of the most dedicated networkers I've had the pleasure to talk to on a reasonably regular basis, and mainly in terms of the market intelligence that he derives from his line of business and the amount of people he's continually engaged with. So it gives me tremendous pleasure to hand the floor over to Simon to introduce himself before Alex and I ask him more about his work, pursuits, and interests. Over to you, Simon.
Thanks very much, John, and good to meet you also, Alex. Yeah, so yes, Simon Nicholson, CEO of Metascube, as John has just mentioned there. So I guess a little bit about my background. So semiconductors originally. So I used to work for Samsung, Toshiba Semi. I also spent several years, 5-6 years, in actually product management, and then moved more into commercial roles as business development director at Cascade Technologies, which was actually working in laser physics, and then also working with AEA technology and battery technology. In fact, actually, AEA, if anybody recalls, actually patented lithium ion, was a lithium cobalt oxide back in the early 80s. So yeah, I've a background 6-7 years with AEA, working with them on a global basis, and then also with working globally with Cascade Technologies. But as John said, for me, it's always about sort of that business development, marketing, sales, a commercial aspect. And clearly, our experience is that, we have an extensive network of contacts, domestically and globally. And we'll talk maybe a little bit more about that in a moment.
No, thanks very much, Simon. And then over the years, we've talked about a whole range of stuff, and
yeah,
I think we could probably spend a good 6 hours discussing everything we've talked about. But do you have any experience in the solid state arena? What have you been watching recently? What's your perspective? Because I know you've got a very broad perspective of what's actually going on in the arenas.
Yeah. So basically, with the client base that we're working with, and a number of those are in the electrification space. Some actually in the US companies, some are in Europe. But basically, electrification of transportation is primarily the sort of one of the sectors of interest for ourselves. So I was just on travel last week and met with half a dozen different companies across Europe who are working in the field of implementation of electrification on transportation products. So whether it's off-highway construction vehicles, etc. And one of the things that I see, and I've always seen actually, is this sort of, I guess I'll call it a fragmentation. You know, every application is different, every power requirement is different, every use case is different, how these assets are used. And, you know, they're continually, as companies we work with and clients that we're working with, supporting these companies to design in some of these solutions, they're constantly looking at the variety of chemistries and solutions that are out there. Because the reality is we've been sort of, for the last, I guess, 100+ years, been, you know, filling tanks with hydrocarbons quite happily, and basically turning the key in the way they go. And the reality is that's no longer the situation going forward as we transition to electrification. You know, there are duty cycles, as I said, and sort of operational use cases, which are determining, you know, what's the optimal solution for said vehicle, whether it's a sub 1 ton unit or a 30-40 ton unit and everything in between. So yeah, there's a number of companies who are working with LFP currently in the construction sector and the off-highway sector. There's a number that's working in NMC 622, 811. I would say in some of the more advanced applications, they're sort of more mindful of sort of these new generation of technologies that will be available, you know, in the near term, and obviously solid state being one of those. But currently, you know, a lot of the applications that we see just on the energy sources, obviously we deal with motors and power electronics as well as thermal systems as well. But just on the energy source itself, predominant chemistries that we see, you know, here today at scale would be NMC and LFP.
Yeah, no, thanks, Simon. I think I can relate to that. And LFP is really coming back into the fray. Alex, as far as I'm aware, your technology will work with a wide array of chemistries. But I think LFP has been one of those you've researched. Is that correct?
Yeah, I mean, ultimately, solid state, it's not it's not really reinventing the wheel or anything like that. Really, there are three main components to the cell, the cathode and the anode, the electrolyte, and all solid state is just an improvement of the electrolyte. And for the most part, you could keep the cathode and anode the same. And so in our case is no different. So, we are chemistry agnostic, and we've demonstrated our technology in LFP and NMC cells. I was asked the other day, what kind of trends do we foresee in 2024 within the battery market? And one of those is definitely going to be even more use of LFP, and LFP taking more share in the market away from NMC. And it's purely on a dollars and cents basis, but then also, some geopolitical considerations, of course, with the specific transition metals you have to use in NMC versus LFP. You really just need iron and phosphate, right? So, yeah, and I think, and when we talk about solid state enabling really high performance, we're mostly talking about pairing this electrolyte innovation with more innovation anode side, not really doing much cathode side. So cathodes have really gotten pretty good. And when we talk about performance bottlenecks, it's mostly graphite on the anode side, and substituting graphite with some other material with more capability.
Yeah, thanks, Alex. That's absolutely. Just for the audience, LFP is lithium iron phosphate. NMC is nickel, manganese, cobalt. Just in case we're talking acronyms that people don't necessarily understand. No, thank you, Simon. Just to clarify, your business is covers a vast array of things. What do you actually offer as a service to your clients, and how does that all work?
Yeah, sure. Yeah, so normally it has a variety of different approaches, or we have a variety of different approaches in terms of the client base. So in some instances, it's basically where we're brought in to deliver the the sort of strategies of the business and the business development of the business, and the execution as well. So for us, it's not about just actually saying what guiding companies and giving them sort of set of strategies in terms of implementation and how they could do it. We actually would do it for them as well. So, rather than sort of giving an action plan and walking away and expecting the company to implement it, then, we would effectively create that in conjunction with them, and then we would execute it as well. Together with their team. It depends on the size of the organization, but some of the companies that we're working with will give you some sort of scale of 500 headcount.
So it's a proper consultancy, not just a I'm confusing the terms, but you know what I mean. You'll actually go in and do the work
correct.
Rather than giving the information and walking away and expecting it to be done. You actually go in, do the work, and implement things. Which
correct. Exactly.
So,
and there's obviously the intelligence that we use. There's a number of different tools that we use in order to engage with customers of clients. But as I say, we tend to work in the technology space. Whether it's semiconductors or power electronics or motor technology, but all in and around sort of zero emissions and the net zero transition. That in itself does. There's certainly plenty of opportunity just within transportation, and in terms of an organization such as ourselves. But for us, it's about being able to implement those strategies, and obviously those strategies may need to be adjusted from time to time in order to, with the insight that we've obtained or the intelligence which we've gathered. It's a constant process of fine tuning, as it were.
No, fantastic. And I guess you have a basic model which you can apply to. There's sort of a white label model that you can apply to whichever business
correct
working with.
There's some sort of core fundamentals that we operate within, and then they're adjusted accordingly, or nuanced accordingly to the clients themselves. So I'd say with some of the scale of the organizations, it's sort of 500 headcount organization, then that's different than the way in which you'd opt it with a 20 headcount operation. So but there's some core principles are there. The guiding principles are still there, but still the execution is obviously paramount as well. Delivering on what we have collectively agreed in terms of targets and measures, etc., etc.
As I say, Alex, that sounds quite interesting for Natrion. Actually, I mean, I think.
I can imagine. It looks really interesting what you're doing at the moment, and what you've done, and certainly, I'm sure we can take something offline and discuss in more detail for sure.
I think now is probably a good time. I'm aware that Alex is having conversations around similar themes at the moment because. I mean, as I said to you offline, Simon, I'm absolutely blown away with what Alex has achieved and what he's learned on the way. And I think now is a really sort of critical point of perhaps reassessment and looking at, wow, look at what we've achieved and what do we need to do in order to sort of take it to the next steps. And I think, from my perspective, the more people Alex talks to about this and gets information, the better position they'll be in.
Sure. It's all about networking, as we said earlier.
Yes. Well, Alex does his fair share of that too.
Good. Actually, I had a question for you, Alex, actually, just in terms of on the technical side. So this LSIC approach that you've got, just maybe expand on that for me a little bit. I'm interested to learn a little bit more about that.
Sure. We principally identified solid state as, well, we really believe solid state is a path forward for realizing desirable mass market electric vehicles, cars that folks are going to want to buy. And at the core, we identified the problem of solid state as being a manufacturing challenge. So, if you really think about it, solid state, we've known about it and its capabilities and its possibilities And for as long as, we've really been commercializing lithium ion for the last 30 years. And the solid state simply hasn't made it to the market because nobody has determined how to make it as manufacturable as lithium ion. So we got really good at making lithium ion batteries using highly efficient, high throughput, high yielding processes. And we haven't been able to replicate that feat for solid state. So, we took a look and we see an industry that is, mostly dominated by a couple of incumbents, companies like Panasonic and LG who have gotten really good at lithium ion, who have sunk billions of dollars into gigafactories that are quite good. And how can we help transition, this infrastructure, these resources towards solid state manufacturing? And so that's what LISIC is it's uh, it's a solid state electrode technology, but where we've combined, all the electrochemical components that you need for solid state with, the mechanical properties that you really need for compatibility with lithium-ion battery roll-to-roll processing. And so what that means is we can integrate into existing gigafactories at a low cost of implementation and allow a company that's already producing lithium-ion batteries to transition to solid-state manufacturing at high volume and at low cost with their existing equipment and capital. So, our hope is such an approach is the way to arrive at market viable solid-state batteries, and that can actually be put into EVs at significant volumes for consumers. So,
Sure. Okay. And I guess at some of the energy densities which you're attaining, then you're pretty much 2.5x current technology, let's say.
No, not quite that much. We've shown how we can realize over 50% improvement in energy density compared to state of the art. And so and so that means either if you have a 300-mile range EV, that now becomes 450 miles, right? And that goes a long way in combating range anxiety. Or you can make electric vehicles with the same range but with a much smaller pack, and that makes them much more cost efficient and accessible to more consumers, right?
Yeah, sure. Okay, so around about 50% improvement. Okay, on current energy density.
Yep.
And is that, are you, I think you've done some pouch cell development work to date, but I guess you've got applicability into cylindrical cells as well?
Yep. So, we talked about being chemistry agnostic and then, form factor agnostic.
Okay.
Yeah, so one of the things that I know nature and the very nature of the name nature and Na sodium. One of the things I got very excited about when I first bumped into Alex and the gang was that they combined the term sodium with solid state. And I absolutely get why nature have gone down the route of lithium ion, because that's where the funding has been and that's where the interest has been currently, and that makes 100% sense. But Simon, what's your view on sodium? Because I mean, from my perspective, I think sodium is a really big player, and I think that Alex is in a really good position, having the lithium ion stuff, but also having the sodium ion stuff going along in the background. What's your take on the whole sodium ion arena, Simon?
Yeah, I think certainly. I guess if I look at in the transportation applications, I could see it in the energy storage, the static storage applications, that it's becoming quite has some unique offerings in that space. And obviously CATL announced they were developing sodium ion, for production capacity purposes, not just for development, but we're actually taking it into volume production. And I think also Northvolt has recently announced about sodium ion as well. So I think you've got some fairly significant organizations that are, certainly in the case of CATL, certainly a significant organization that's identifying, different chemistry for different applications. I guess as we see a little bit softening in the market on, so let's say, EV vehicles. I think you were seeing that in Europe, and I'm reading up that in the US as well a little bit. Then that will create further focus on energy storage, because basically the capacity for the cell manufacturing is coming out of China currently, and there is a very significant capacity which they have both currently and planned, which is driving the global economy somewhat on the electrification side. And they've been working with LFP as well as NMC for a period of time, and that I think they're starting to see, with the announcements from CATL, that engagement into the sodium-ion space as well. So again, like I was saying before, it's almost this fragmentation of the applications, seeing a little bit of fragmentation of the chemistry depending upon the application. So certainly in static storage, I would certainly see sodium-ion capturing market share. Certainly, just as an example, one of the clients I met with last week, customers, should I say, or client, then they're in transportation, they're manufacturing vehicles, it's privately owned, it's about 10,000 units a year. Quite a successful company, only been going 20 years. And, the engineer's telling me, hey, we need to be at 300 euros per watt hour, kilowatt hour. So we've got engineers, getting guidance about where the price needs to be in order for their platforms to be competitive. So, I think it's not just coming from the commercial departments, it's coming right across the organization, about driving this need for competitiveness, and the battery clearly is an integral part of that overall cost, quite a significant integral part of that overall cost of any system. Their units, so on the 5-ton units, they sell for 250,000 euros each. So it's a significant proportion of that is, the drivetrain, as it were. So anything that's improving the cost, and clearly sodium-ion, indications are that it will improve the cost base because of the abundance of the materials, etc. Then that's another driver, just as LFP's creating and carving out a market. It's because of the competitiveness of the solution. It's got some advantage. You can run to 100%. You can get some additional life cycle out of the packs, but there's a financial aspect to it as well, which is driving the adoption, as you were saying, Alex. It's the same in EVs as well. There's plenty of cars in the 30, 40, 50,000 euro, well, I'll say sterling price mark in the UK. There's not so many 10 to 20,000 sterling pound price cars that are EVs. But again, China they're starting to influence European automotive manufacturers, with the increase in activity and the deployment of their cars into those markets. Holland's actually been a beachhead for a number of them, actually, for a number of years, just as Norway has been a beachhead for a lot of the Chinese manufacturers, and EV manufacturers, particularly Chinese origin, has been a big beachhead for Tesla for many years in Norway. But I think that dynamic will change, and the EV incumbents within Europe, shall we say, this additional pressure which is coming from vehicles coming into the marketplace.
Right, thank you. Yeah. I mean, I think the whole sodium-ion in EV is a really interesting debate. I mean, I completely agree with you. I think the certainly the first application has to be stationary power, and has to be, because currently the energy, the weight is almost twice, significantly more than that of a similar energy density lithium equivalent. But if you've got and size as well, but if you've got space and it's not moving, then it's not a problem. And if it's cheaper, then it's good. But I mean, I'd be interested, Alex. What do you think? Do you think if you're able to put solid state into sodium ion, would you get anywhere near the lithium ion capability of volumetric or energy densities?
Yeah, sodium for sodium, solid state is definitely an enabling technology. I think the consensus at the moment is we can draw near LFP type energy densities with sodium. Now, when it comes to batteries, right, there's the tricky thing with batteries, there's a whole bunch of things you really need to optimize. Energy density is just one piece of the equation. You can have energy density, but if you only have a few duty cycles of lifespan, it's still not a viable battery.
Yeah.
Or very low power density. If you've got very low power, if you can have extremely high energy density, but with low power density, it's yeah, equivalent.
Exactly. Yep. And yeah, with sodium, the tricky thing was the anode and the cathode for a while. And significant, so for example, right, graphite is used in virtually every lithium ion cell right now. You can't use graphite in sodium. Sodium ion is too big to shuttle into graphite. So you have to use hard carbon, which has much poorer duty cycle life than graphite in comparison. And subsequently, the lifespan of a sodium cell uh, wouldn't be able to approach what we come to expect from lithium. Um, so solid state, like I mentioned, solid state, even though you're innovating the electrolyte, solid state allows you to use alternatives to regular anode materials. And in lithium ion, that's how you get higher energy density with solid state. Is solid state lets you use something other than graphite, for example, silicon or lithium metal. And at sodium, it's similar, where solid state enables you to use sodium metal or some alternative higher energy density anode materials. And that's encouraging because sodium, we actually have started to figure out the cathode side. Originally, it was a similar problem. You couldn't make a sodium analog of LFP, and you couldn't make a sodium analog of NMC because those were unstable materials. But we have since developed great sodium cathode materials, and it's really the anode side that hasn't caught up. So our hope is actually with solid state and using alternative materials anode side, we can actually surpass LFP energy density and have something viable for EVs. Because the truth is, if you look at everything we want to accomplish in electrification with energy storage, there's simply not going to be enough lithium in the Earth's crust. And unless significant progress is made in lithium recycling, sodium is definitely going to have a massive role to play in electrification.
Oh, wow, fantastic. Just quite naively, how easy is it to produce sodium metal? I mean, does it exist in nature? I've not come across.
Yeah, I mean, well, how easy is it to produce lithium metal? It's
Yeah,
not, but we
yeah,
figured it
yeah,
out. And because lithium metal, was used in primary batteries, non-rechargeable batteries, forever.
yeah,
And we're taking that know-how and actually combining that even with semiconductor manufacturing know-how, and now making that work for lithium metal cells. And a lot of that's going to be transferable to sodium metal. Sodium metal is, a bit of a different beast. It is even more challenging in many respects to lithium metal, but most of it's transferable. And uh, people, I think when you hear about sodium or lithium metal, you think about those videos of people chucking chunks of sodium into water or something and it blowing up. The
yeah,
reality is when we talk about sodium metal in a cell, we would use something like 5 or 6 micrometers of sodium. Put that in perspective, human hair is like 75 micrometers thick, something like that.
yeah,
So it's
yeah.
it's it's a really tiny amount. And it doesn't really, in some ways, actually, a sodium metal cell can be more safe than a sodium cell using a carbon-based anode.
Well, that's interesting. Yeah, no, very interesting, and yeah, certainly a lot of food for thought for the future, and really great to hear that you're already beavering away in the background to be there when the time's right.
One of the things that we're seeing as well is a lot of in the transportation space. And we're talking non-EV here, but everything else, So we work in anything from two-wheel to steel wheels, from train all the way down to two-wheel vehicles, scooters, and everything in between, and say hypercars, etc., etc. One of the things that we're seeing is the transition to higher voltages as well. When we say higher voltages, we mean about 700, 800 volts. maybe 700 volt nominal. But there is also a sort of community there that is moving to higher, lower voltage. In other words, they're moving from 48 volts to 96 volts, but they're still within the boundary of low voltage. And a number of the reasons why they do that, they'd like to maybe go higher if they had a choice, but it is because of their end customers wanting to, from maintenance perspectives and, sort of just the additional layers of protection which are needed when you're working at higher voltages. But what's your thoughts on that, Alex, as you go forward with the with the solid state?
Yes, it's a great question, and to be honest, yeah, we probably should know more about implications at pack level integration than we currently do. And so it's not a familiarity of ours, just because just to be clear, right? So we don't even plan to be a cell manufacturer. We really just want to make our solid state electrolyte active material for fully integrated cell makers. And so we do cell level R&D because the burden of proof is on us to ultimately show the merit of our tech and being an enabling technology for next generation chemistries, and show the OEMs how they can implement for the greatest or most impactful effect. Pack level integration, I mean, it's I hear about BMW going to 800 volts and this and that, but honestly, I don't know too much about it. But
No, I can relate to that, Alex. Having spent a while in the battery industry, somebody then presented me with a pack question. I was like, what's that? We just make cells,
Yeah.
That's what we do. What they do with them, not our problem.
Yeah. There's obviously benefits in going to higher voltage. This is reducing sort of the real estate and some of the sort of dimensions of the cables and some the diameters of the cables and so on and so forth. But it's interesting that certainly in some of these organizations' timelines, in the next 5 to 10 years, then some are saying, yeah, we're going to move to 96 volts, but we won't, or we don't envisage moving to higher voltages beyond that because of other factors, say customers' acceptance of the high voltage, maintenance challenges and perception, I guess, almost by their customers in terms of how their operators will be able to accommodate higher voltage systems, whereas other ones are saying, no, we will have a proportion of our manufacturing output. I'm talking one particular that we deal with, that's about 25,000 units vehicles a year, and they're going to move to about 30% electric. They're currently about 10% electric, but it'll be 30% electric by 2030. And all their platforms, and I say all, there's another 4. They've got currently 1, but another 4, which will basically achieve that 30% of the total production, are all going to be 800 volt platforms. So they're immediately stepping from currently low voltage, stepping beyond 400 straight into 800. Because there's advantages that they can see in terms of the operation of their assets. And I say these things are ultimately, as I said, determined by their use cases and the duty cycles that are applied to them. But the largest vehicle they do is a 14-ton unit. So everything, in 3-ton, 5-ton, 7-ton, all the way through to 14. They do see fuel cells actually 10 years out, but it's basically batteries for the next 10. But they can see, the glimmer of light of fuel cells as being a potential integration option. And we actually deal with another company who's in mining trucks. So and what they're doing is basically currently is a fuel cell together with a battery. So again, as I said, it's these different approaches, different needs. And I guess when you're hauling 200 tons of material, then, and you're running those things pretty much 24/7, then you've got a lot more challenges than you have of something that's working in a municipality, repairing the roadway or the pathway, and is working for an 8-hour shift. But I say they're just fundamentally the differences.
Yeah, there must be a huge algorithm of calculations that would
Yeah.
have to be applied to like a freight company who
Mhm.
already have a massive algorithm of how they save fuel on
Mhm.
every one of their trucks that's delivering, to then have to translate that into an electric. Did you know if any of the companies are already working on those algorithms, those models, or?
A number of them have information. Obviously, some of them are some of these assets, and more actually having telematics on the assets. So they're basically gathering that data
Yeah,
on an ongoing basis,
yeah,
and more data, more specific data. But maybe just as an example, one particular application that we work in is it's a 200-ton truck, and it's 900 volts plus or minus 200. So, just on the motor, that's challenging on the motor.
yeah,
And that potentially is operating about 4,000 meters altitude as well. So there's different considerations in terms of the architecture of the electrical system, in the motor,
yeah,
because of the when you're working at that sort of altitude. So there starts to become, as I say, a lot of information which you need to look at in order to make the assessment of what's an optimal solution, and where there may well be some adjustments which the customer can make. They may come out with a wish list sometimes, and you're looking to get some clarity on what is the real need. There's a nice to have and a need to have, and the need to have is what we're trying to get to, because and then customers are obviously highlighting that to us as well, as that they can see it's challenging for some of these applications. It's challenging in terms of some of the specifications which you're looking for, and normally that provides a little bit of flexibility in their requirements, because it is effectively a wish list which they've got. If there was an ideal scenario, then this is what they'd be looking for. But the reality is, some of those scenarios aren't available, not today.
yeah.
And that's across the system, from the power electronics to the motor technology to the battery technology, etc. And so they're having to compromise a little bit. But yeah, some of the data which they've got, they know, in broad terms, what functions the machines are using at any point in time. It's 20% of this or 10% of that. It's lifting the boom, it's traveling along a horizontal, it's got an incline of X that it's going through. But the reality is that there's, as you say, there's more data that needs to be collected. But they've normally got some parameters by which they're working to give that application, some perspective in terms of what the system needs are.
Yeah, fantastic. Thank you, Simon. Yeah, we're at about 3 minutes left now. Is there any burning questions either of you have for each other?
I mean, it's, I always love kind of, like I said, we're kind of hunkered down and focused on the sell side. So it's always great to get the perspective from, I don't know how to call it, the actual powertrain side and
Yeah.
and the broader macros. I guess what I'm curious about, Simon, is your perspective on kind of a 800-pound elephant in the room, right? Is charging and infrastructure, because you talk about like Class A vehicles, these have to be charged with basically megawatt charging, right?
Yeah.
And the infrastructure required for that is immense, and especially here in the U.S. where our electrical grids are all 100 150 years old. It's going to be a significant challenge. You can put out as many electric vehicles as you want, but if especially larger commercial vehicles, but if you can't charge them, what's the point? I'm wondering what your perspective is on that, and whether it's an optimistic one or, or perhaps a pessimistic.
I think again, I think it's all down to the use case. So it depends on the asset. So let's say it's a 200-ton truck. If we start at that, as we've just been talking about, then what they're doing currently, not in all applications, but a number of applications, they basically put them on a trolley line. So basically, as the vehicle is traveling in the region it's operating in the mine, and let's say it's an open mine, it's not an underground mine. I'll come on to the underground stuff in a second, but let's say it's an open mine, then because the trucks are traveling a certain route and they're traveling that route repetitively, that's where the plus or minus 200 volts comes from, what I just mentioned before, because basically that's when they hook up to the overhead. So they basically take direct power from the grid, and they use that as a means by which, when it's traveling 500 meters up one route and it's connected to the trolley line, it's actually charging the battery at the same time. Because there's then a question of, they can't have the asset idling being recharged, because it's losing money when it's making money, when it's working, not when it's not working, as it were. So that's one approach which has been taken. And the other approach is that, sort of at the smaller scale of some of these vehicles, then the clients are buying complete systems from the companies that we're dealing with. So they're buying the charging infrastructure as well as the vehicle. So it's a one-stop shop, as it were. There's other clients, again, some of the companies I met with last week, that they've basically designed cradles, and these are 9-ton excavators, wheeled excavators, and they have basically the ability, you switch the pack basically. So you sell, for every vehicle, you sell 2 packs. One's being charged and one's being used, and then you basically physically remove the pack, from within the cradle. So the packs are in the cradle, about 400 kilowatt hour packs, or about 150 kilowatt hours each, up to about, I think it's 400, 450, and then basically that is removed and replaced onto the vehicle, and the vehicle carries on operating. So the part of the use case there is they don't want the vehicles coming back to a location which is too far away from where the vehicle's operating. So it's easier basically to have the packs locally in the cradles, fully charged, ready to go, and those to be switched out in location, rather than the vehicle traveling, a kilometer back to a charging station, because that's where it's, connected to the grid or whatever. But then there's other systems. I know there's a number of companies who have basically 350, 400 kilowatt battery packs in the charging station, and the battery pack is being used as a means to supplement the grid where there's limited grid capability. Then they're using that as a local boost to basically, charge the assets. So they've got their multiple charging stations, 2, 3 charging outlets on the station, but they basically got battery pack systems installed within the charging infrastructure. So there's it's a number of different approaches to solve the problem. And then you've got other, direct hydrogen. JCB in the UK is working on direct hydrogen engines, so they use bowsers of hydrogen. So there's store tanks on the assets, on the backhoes. And if you look at a direct hydrogen engine, it's pretty much the same as a conventional combustion engine with a different top end. But fundamentally, the challenge they've got is, getting the distribution of the fuel, i.e. hydrogen, to the location where these assets are operated. But typically something that's like a backhoe or some of these construction vehicles at that scale, they're fairly mobile. They're moving around quite extensively. But if you go to a 900-ton excavator sitting in a mine in, maybe South America, or South Africa, or Russia, or whatever, with a 37-ton bucket on the front, that sits there all day doing the same function. And what they do there is they basically put 11 kV straight into the back of the asset. So they power it straight from the grid. It's on a tethered, so it's on a reel and tethered off to the grid. So it doesn't have a lot of movement, but other vehicles are a little bit more, because of the scale, the smaller scale, 5-ton, 10-ton, they are very mobile by definition. So again, it's this fragmentation, because the application drives the system spec. The system spec is driven by how the user operates the vehicles and how they utilize those vehicles, how long they're using them for, 8-hour shifts, 24-hour shifts, 7 days a week, et cetera, et cetera. But what we always say is, it's voice of the customer. It's so important to understand each of these applications and be talking to the people who are making those decisions. And in our world, it's engineers. We'll talk to the technical folks before we talk to the commercial people, because we really need to understand how it's being used. We can have a commercial discussion once we understand what the parameters are, the boundary conditions. But it's no point having that sort of commercial discussion before you really understand, what what are the boundary conditions, what are the flexibilities in those boundary conditions, what are the hard and fast must-haves, and what are the nice-to-haves. Hopefully that's giving you some guidance.
No,
Uh,
that's very insightful. Thank you.
Thanks, Simon. We better wrap it up and conclude now, but it's been
Right.
really interesting. Simon, thanks very much for joining us today.
Hey, welcome.
There'll probably be some further discussions
I'm sure there will be.
afterwards.
Yeah.
But yeah, so thanks very much to our audience. Hope you enjoyed this session. We look forward to seeing you again next session.